Okay. So in general, okay, these numbers are of high importance because they can allow you to make some general conclusions. And for example, okay, when we talk about Reynolds, let's say you have flow, for example, in ducts, let's say, okay, you have flow in circular ducts. Um, if you want to characterize the flow, you can, let's say, divide between laminar and turbulent flow. To do this classification, you can talk about values of Reynolds number, which is a dimensionless number that can have indication about the type of the flow. Because if Reynolds, which is rho v d over mu, is smaller, let's say nearly than 2,300 from experiments, you can say that it's a laminar flow. And if it's larger than 2,300, so you move to turbulent flows. And what is nice about Reynolds is that you can have variation of these four variables in different ways in a way to give the same number. And if you have Reynolds equal, let's say, to 2,500, you have a turbulent flow. This can be caused by, for example, or increase in velocity, or decrease in or increase in diameter, or decrease in viscosity. So you can play with different parameters while reaching the same result. That's why we say dimensionless number are general, and they can come from variation of, let's say, one of several variables. So by varying one of these variables, you can play with the Reynolds number. And this is why in experiments in general, we talk about groups instead of one variable. And instead of saying, for example, if I want to study if flow, instead of varying rho, vd, and mu, it's enough to vary v, because this will vary the Reynolds number. So from here the importance of dimensionless numbers.
Yes, doctor. So to determine the formula of the Nusselt number,
Yeah,
we should check if the flow is turbulent or laminar. And to do
of
this, we
course,
have to get the Reynolds
exactly.
number.
And to determine this, we check for Reynolds. Yes,
Yes.
that's it.
Okay.
Okay, look, you don't have to memorize any relation, you just have to understand the concept. So for example, I can give you in a problem a set of empirical correlations, and I tell you, if you have a and I will tell you, let's say, for Reynolds smaller than this value, you consider the flow laminar. For Reynolds value larger than this value, you have a turbulent flow. Then I tell you, if the flow is turbulent, so for this range of Reynolds, you use this empirical relation for Nusselt. For other range, you use another range. And from here the importance of this work, because once you do experiments, let's say researchers can give you like graphs or empirical relations that you can use in any case. Okay, and if you have any similar let's say problem, not even you don't have even to have same dimensions or same velocity, you just have to ensure that you have same Reynolds number. Because once you use the empirical relation, you say, for this range of Reynolds, I can use this empirical relation and it will be valid. Okay,
Yes, clear, doctor.
welcome. Other question? Okay, so look, today I will introduce for you chapter 3. Okay, chapter 3 is a very important chapter because it can, if you want, link the knowledge, if you want the knowledge from thermodynamics and how we deal with cycles, with the energy conversion from one form to the other. And by understanding how we deal with the variables in this chapter, we can then study several energy systems. You can study, let's say, the performance of thermal engines. You can study refrigeration systems. You can study systems of steam turbines, gas turbines, etc. So I will introduce now the concept, and during this week, you can go over chapter 3, so we can start also to do some practical example on it. So to start with, whenever we talk about a closed cycle, we have a number of processes that will be repeated. Okay. And from here, we can characterize, let's say, the different points of the cycle and determine how the system is exchanging with the surrounding in terms of heat and work. For example, let us start from an example to understand what we'll do in this chapter mainly. If you take the system of combustion in cars, okay, this system is based on a very simple combustion process. What will happen is the following. Let's say you have the cylinders. Okay, you have your cylinders, and at the top, let's say, of your cylinder, you have valves that will allow air to come in. Okay, and so you just operate your valves. During admission, let's say you open the valves to have intake of air and the fuel. Let's say if we consider first the intake part, then what will happen? Your piston, okay, this is your piston. Your piston during the admission will move downward, and you know that your piston is connected to the crankshaft. So it will move downward, and we have the admission phase. Okay. After this, you will start to compress your mixture. So when your piston is here, let's say admission is done, you have air and fuel inside your cylinder. You will compress, so you will move your piston upward. You compress the mixture. Once you have a high pressure and temperature, you can give the electric spark, let's say, to cause the combustion. Okay, and because of combustion, energy will be released, and due to this energy, you will have a high pressure and temperature inside your system, and you will have force that will push your piston downward. And at the end of combustion, you will open, let's say, the exhaust valve, and air will and exhaust gases will go out of your cylinder. So this is in summary one process that you might have. If you want to model this process, okay, you have several complex issues in reality, but you can try to model this system in a simple way. Okay, let us try to see what is happening to air. If you want to draw on a graph what is happening to air, let's say we want to draw, for example, the variation of pressure with volume, for example. Okay, you want to draw on a PV graph what is happening. We can do some, if you want, assumptions that can simplify the models. For example, one assumption that we take in modeling is to say, I will not consider that I have an admission phase and an exhaust phase. I can consider that it's the same mass of air, let's say, and this mass of air is subjected to a cycle. So I compress it, okay, then I have combustion, but instead of this the combustion, which is, let's say, the spark, I model this just as giving heat to my system. So I give heat to my system, and after this I have expansion of my piston. Okay, and I can model, let's say, exhaust of gases as, if you want, rejection of heat. Okay, so let us try to draw this. Let us try by the compression phase. Okay, so consider your piston is here, and now you want to compress air. What will happen during the compression? What will happen to your pressure during the compression phase? When you compress a gas, okay, what will happen to pressure and volume? No idea? So if I start, let's say, if I start from point 1 here, this is point 1, okay? I have a certain volume and certain pressure. Yes, Seth, exactly. So the pressure will increase and the volume will decrease. So when I go from point 1 to point 2, I have I will move on a line, if you want, in a way that the volume will decrease and the pressure will increase. Now, if I consider in my modeling that I am not losing heat to the surrounding, okay, this is a good assumption, maybe because let's say we can use well-insulated material to profit to the maximum from the combustion process. So you have like in adiabatic process. When we say adiabatic process, this means that no heat loss. So if I tell you we can do as modeling assumption that no heat loss with the surrounding, then we can consider that this phase from 1 to 2 is adiabatic. Okay, so we have an adiabatic phase. Whenever we say adiabatic phase, then Q is 0. Okay, so the characteristic of an adiabatic phase is Q equals to 0. Okay, so this is our first phase, phase 1. It's adiabatic and it's characterized by Q equals, so it's adiabatic. Okay, then no heat flow between the air and the surroundings, so Q equal to 0. After this, once we reach the top level, we are at the maximum pressure after the compression. We reach the maximum pressure of compression. Then we say now we are ready to have the combustion. To model combustion in a simple way, okay, we can consider its heat addition. And when we add heat to the system, we can add it in several ways. And for example, let's say I can give you this information in the example. For example, I can tell you, let's say for gasoline, we can model combustion as heat at constant volume. We had heat input at constant volume. Why it's a good assumption? Because in general, what will happen in gasoline engines, when you reach the maximum level of the piston, you have the spark, and just before reaching this level you give the spark, uh, which will induce combustion. And because this process is very fast, then you can consider that it's nearly instantaneous, and it's taking place at nearly constant volume. So you can consider that you are gaining heat from 2 to 3. You can consider that you are gaining heat at constant volume because you can treat it as instantaneous process. Okay, so here you have an input Qn to your air, or to your system air plus fuel. Okay, and after this, what will happen after combustion is done? Now, under the effect of the high pressure and temperature, the piston will be pushed downward, and this will lead to the expansion phase. So you have also an expansion phase that also can be treated as adiabatic if you ignore, if you want, the heat loss from the cylinder to the outer environment. Of course, this assumption is not true. You have losses, okay? But if we do this assumption, you can just do first like a first model of your system. And always after this, we compare with reality. And when we compare with reality, we can, if you want, come up with some correction factors that can allow us to, by modeling, to get accurate results. So here we can consider that we have an expansion phase, also adiabatic. So it's adiabatic phase, so Q is 0. But of course, during this phase, this is the most important phase for us. You know why? Because what is our purpose here? Our purpose, whenever we have the thermal engine system, our purpose is to drive our car, okay? And what will happen is that this force will displace the piston with a high push, and the system of rod crank will transmit this force to the crankshaft, and then you will have rotation of your crankshaft. Okay, so this is the most important part for us, because during expansion we'll transmit a force to the piston, and from the piston will create a couple of rotation on the crankshaft, which will allow us to operate our car. So here mainly is the work output. So our system will deliver work at this phase. In chapter 2, we have introduced this concept, okay, for cycles, how we calculate, let's say, the work, how to relate work and the Q. Because if you remember, whenever we have a closed cycle, okay, so the last step here, I will talk about the equation after we describe the whole cycle. So this is the third phase, if you want. Between 3 and 4, you have the expansion of your system, which will produce work. And finally, in the final phase, here we model the exhaust part as rejection of heat. So we consider that we have rejection of heat also at constant. We can consider it at constant volume. Okay. So what will happen then is that we have Q out here at this level. So now, and then the process will be repeated to continue to produce work in a continuous way. So this is a closed cycle, a repetitive cycle. Okay, if we want to do the analysis, the energetic analysis of this cycle, we need to determine, let's say, the efficiency, what is the work output, etc. We can write the energy balance for this system. uh, Angelo, do you have a question, or you were just answering the question? If we have constant volume, yes, it's an isochoric process. Whenever you have constant volume, it's isochoric, and you can have increase in pressure or reduction in pressure depending on the phase. Yani in the combustion phase, you have increase in pressure at constant volume. In the rejection of heat, which represents the exhaust phase, you have the reduction in pressure, and heat is rejected by the system. Okay. Okay. Now, whenever I draw my cycle, if I want to do the energy balance on it, whenever we have a closed cycle, so I start by a point and I go back to the same point, then I can write that delta of energy is 0, because I'm going back to the same point. So delta E is 0. Now, the energy of interaction of this system with the surrounding, okay, can be in terms of heat and work. So I can do the analysis of the different phase. From 1 to 2, Q is 0, because they told me it's adiabatic. So I can write now sum of Q plus sum of W equals to 0. Okay. Now, I talked, if you remember, in the course material about the convention. So in some books, you find the balance is written as sum of Q minus sum of W equals to 0. You can use the conventions that you want. I don't mind. You can use the ones that you prefer. The whole idea is the following. You should pay attention whenever you use a convention, okay, to know how to put the work. What we mean by this, in some cases, they consider that the work is positive when it is produced by the system. And for example, here, this system is producing work because it allows us to drive the car, okay? So in this case, they consider that W is positive. But when you want to write your energy balance, this flux is getting out of your system. Because it's getting out of your system, it will reduce the energy of your system. So it should be treated then as a negative flux. That's why if you consider that a work is positive when it's produced by your system, when you write the energy equation, okay, then you should put sum of Q minus sum of W equal to 0. On the other hand, if you consider that any flux coming in is positive. So if the work is done on the system, I consider it as positive. And if it's produced by the system, I consider it as negative. Then you can put sum of Q plus sum of W equals to 0. Okay? So now let us follow this convention because it's easier to work with. Everything getting in the system will add to its energy. Everything getting out of the system will reduce its energy. So if we do the analysis of this problem, okay, we can say that in this case, sum of work, okay, is equal to minus sum of Q. And we can find, let's say, the network produced by the system, okay, and you will get a negative work here because you are losing energy from the system, so you are producing work. And in case the convention was minus, so if you put sum of Q minus sum of W equals 0, you can get a positive work. And you say, because I considered the second convention, I get a positive work because my system is producing work. Okay? Now, if we want to do the analysis of sum of Q, what is happening here? From 1 to 2, I considered in adiabatic phase, so Q will be 0. Also, from 3 to 4, I have an adiabatic phase. I only have heat exchange from 2 to 3 and from 4 to 1. So I can say that sum of Q here is equal to plus Qn, because between 2 and 3, I give energy to my system. And this energy from 2 to 3 is represent what? It's the energy of combustion. Okay? So from 2 to 3, I am gaining energy. My system is gaining energy. The air temperature and pressure will be higher, okay? Because it will take energy of combustion. So I have plus Qn. While during exhaust, I'm losing energy. So it's minus Q out.
Doctor, here Q is the energy in joules, right?
Yes, exactly. It's the energy in joule. And from chapter 2, how you compute this energy? What do? You do integral if you want to do the general formula, okay? If you want to find the work, you do integral PDV. So if you want to find the work during a certain phase, you do integral PDV, okay? So the network, if you want, in this system, which is integral PDV, will be the area under your graph. So the area of this graph will represent the network, okay? And for units, P is pressure. It's Newton per meter square, while V is volume. So the unit of V is meter cube. So when you multiply Newton per meter square times meter cube, you will get the unit of Newton meter, which is the unit of work. Okay, the work of a force is a Newton times meter, so joule. To obtain what, you should divide by time. So joule per unit time will give you what? Okay. So here, what can we deduce here? The network produced in our thermal engine, okay, is equal to the combustion heat, so the energy released by combustion, minus the energy that is lost by exhaust gases. And if I ask you, what is the efficiency of this system? What is the thermal efficiency of this system? Always the efficiency is defined as what? The efficiency is defined as the useful output, okay? So if I want to write the efficiency, here what will be the efficiency of my system? I am producing a work, okay? So it is the net work, W net, that I'm producing through my cycle over the input of energy I am giving. What is the input here? It's the energy of combustion. So I should divide by Q combustion or Qn. And as we have seen together, W net is the difference between Qn and Q out. So it's equal to Qn minus Q out. So when I do Qn minus Q out over Qn, I get the efficiency of my thermal combustion engine system. And to calculate, now I can simplify more. Okay, Qn will, so I can write 1 minus Q out over Qn. You know that I can increase a lot of my efficiency if I do what? Can you give me an idea to increase my efficiency? What can I do to increase my efficiency? Look, exhaust gases, okay? Exhaust gases have very high temperature. And of course, if I'm talking about the car, maybe in the car, uh, I have, yani, my car is moving, so I cannot, if you want, benefit a lot because exhaust gas will go out. But let's say during winter, okay, during winter, if you have low temperatures and you want to operate the refrigeration, the heating system in your car, no need to consume energy or fuel. No need to consume fuel to operate it because you can just benefit from the exhaust gases. If you just can pass by before exhausting these gases, if you can pass by, let's say, pass them in a heat exchanger, okay, you can supply air inside the car at a higher temperature, and you can verify this in your cars. During winter, if you don't, even if you don't put the AC on, if you just let's say put the fan on, it will draw air from that can take energy from exhaust gases, and you will have blowing of warm air to your inside your car. So you can benefit from this energy that is going out, and you are not using it in another way. This is what we call the process of heat recovery. Heat recovery can increase a lot the efficiency because here, if you are able to use this amount of energy, you can increase a lot the efficiency because you can benefit from the last part. So you can operate another cycle in parallel and taking this Q out as an input to the other cycle, which will allow you to benefit the maximum from any waste or any lost energy. So whenever we use heat recovery, the efficiency of our system will increase a lot because now let's say, okay, instead of saying that the useful energy is only W net, okay, let's say if you are able to benefit from a certain fraction of Q out, of course, you cannot take the whole energy, you'll always have losses. But at least if you just take a fraction, so let's say if you benefit by 50% of Q out, for example, if you are able to take 50% of Q out in order to be supplied, let's say, to the heating system of your car, then the efficiency will increase because when you want to calculate here, you will add to W net plus the recovered part, and plus Q recovered over Qn, which will increase the efficiency of your system. In this chapter, we'll see how we can combine several cycles in order to enhance their efficiencies. So this will be one of the scopes of the chapter. Okay, and we'll study different systems. So I gave you the example of the thermal engine system, I can give you another example, the HVAC system, the refrigeration system. Any, you know that HVAC systems can operate during winter and summer. What is the concept? You have a cycle. So the components of this cycle are the following ones. Let's say you have a fluid that is circulating in the following components. You have a condenser. You have a, let's say, a pump. You have an evaporator. So this is the evaporator. This is the condenser. Here, the same cycle can be used for several purposes by just changing this device. So here we use what we call the throttling valve. And we'll understand what is the difference. We'll describe the systems and we'll see what is the difference. So this is the throttling valve. And sometimes, in case we don't want to use the system as HVAC system, we can replace it, but we can replace the throttling valve by a turbine. I will describe in summary what is the idea. So this is a possibility. Another possibility is to have here a turbine. Okay. Now, which one to select depends on the final purpose of the system. Okay. So, in case you need to create an HVAC system, heating and ventilation, air conditioning system, then your purpose will be to extract heat from a relatively cool place and reject this heat in a relatively warm place. For example, let us take in summer. In summer, the outer conditions, the outer temperature is nearly 30 degrees, for example, or let's say 35 degrees. And inside your room, the temperature, let's say, is 28. But to be comfortable, you need to decrease it to a comfortable range. Let us say 24, for example. So what you want to do, you want to extract heat from your room and reject this heat outside. But the problem is that the temperature here is lower than the temperature outside. And by nature, heat will flow from highest temperature to lowest temperature. Okay? This is why you cannot create cooling effect, let's say here, without external intervention. To be able to reject heat from lowest temperature to highest temperature, you need to create a system where you put work. Because if you put work on a system, here, what is the type of work you put? It's the electrical, first you put electrical energy, because electrical energy will operate your pump. And your pump will play the role of changing the pressure of your fluid from one level to the other. And by increasing the pressure of your fluid, you will allow it to operate at the condition you need it to operate at. What do we mean by this? Okay. In thermodynamics, now when we will study together how the cycles, okay, we'll see that each fluid can operate in a range of conditions where it can go from, let's say, liquid to vapor, or from vapor to liquid. Okay. Whenever you increase the pressure, when you have a certain fluid and you increase its pressure, it can evaporate, okay, at, let's say, a temperature different than the one that, at which it will evaporate at ambient conditions. So let's say you have ambient condition and you have water. You know that for P equal 1 atmosphere, okay, water will evaporate at 100 degrees. And we are familiar with this condition. But do you know that if I decrease the pressure of water, if I decrease its pressure, I can force it, then it will be able to evaporate at a smaller temperature. Let's say if I have P much smaller than 1, I can maybe reach, depending on the temperature I want, I can make it evaporate, let's say, at 20 degrees if I reduce the pressure enough. So from here, the idea of this cycle. Why? Because I want, for example, here, I want to reject, I want to take heat from the cooler place and reject heat at the level of high temperature. To do this, I can put the evaporator, I can put, let's say, my evaporator, okay, at the level of the room, inside the room, because at the evaporator level, what will happen? My fluid will take energy, okay, because it will take energy to evaporate. So all I have to do then is to put a pressure here. I should impose a pressure on my fluid to force it, okay, to force it to take heat at this temperature. Yani I put it in a way to evaporate at a temperature such that the room can give it this heat. So it will take the heat from the room, and after it will take it from the room, okay, what will happen is that I want to again repeat the cycle. Yani, okay, my fluid will take the heat, it will evaporate, it will reach, let's say, a certain state, but now I want it to go back to a smaller pressure because I want to operate the same fluid. Because I want to operate the same fluid, now I want to take it to, again, to a smaller pressure to be able to, uh, if you want, reject this heat. So I took the heat now. I will go to a smaller pressure. As I go through the condenser, in the condenser, I will reject the heat I have taken from my room. That's why the condenser should be at the, I will put it on the side where I want to reject heat. Okay, so I will reject heat at this level. Then the temperature and pressure of my fluid will drop. Okay, sorry, the in the condenser I have a change of phase, so the pressure dropped because of the throttling effect. Now in the condenser, okay, let's say at the I am operating at the same pressure but I am cooling, so I will cool my system and I will reject heat, and now my